Maybe full screen.
Yeah. Yeah, it looks good now.
Yeah. Okay.
Okay.
Gaurav, are you ready? Okay. Good afternoon, everyone. So welcome again to our Special Functions and Number Theory seminar. Today's speaker is Aritram Dhar from University of Florida, Gainesville. He's a student of Alexander Berkovich and is completing his PhD soon. So he'll be talking on extension of Brasu's generalization of Borweins conjecture, some exact results and applications. Yeah, over to you, Aritram.
All right. Thank you. Thank you, Professor Dixit, and thanks to Dr. Bhatnagar and Dr. Krishnan. So all of you are organizing this seminar, which is quite nice. But the thing is that I whenever I'm in the States, it's quite difficult to attend this online every week at 6 because it's like 6 or 6:30 in the morning there. But yeah, sometimes I try to attend. So yes, today I will be speaking on extension of Pressoud's generalization of Borweins conjecture, some exact results and applications. So this is based on two works which I did with my advisor, Professor Berkovich, since the past couple of years. And here is a picture of Professor Berkovich. I'm sure many of you will be knowing him uh, or have known him over the years. So he's standing in front of Mysore Palace, and this was taken in like 20 years ago in 2005 when he was in India for the Shastra Ramanujan conference. All right, so I will start with preliminary background on partitions, which many of you will know, of course. So a partition for me is a non-increasing finite sequence of positive integers, lambda 1, lambda 2, up to lambda k, where each of these lambda i's will be called the parts of the partition. For example, if we look at the number 5, then 4, 1, the tuple 4, 1 is a partition of 5. And the number of parts of the partition will be denoted by this notation nu of pi, and the largest part of the partition pi will be denoted by L of pi. And the sum of all the parts of pi is called the size of the partition, or sometimes you say the weight of the partition, and it is denoted by this notation of absolute value of pi. And we say that pi is a partition of n if absolute value of pi is n, or the size is n. And P of n will be the number of unrestricted partitions of n, by which I mean number of all partitions of n. And phi will be the empty sequence, which is the unique partition of 0. So if we consider the number 5, then there are 7 partitions of 5. So P of 5 is 7, and these are the 7 partitions: 5, 4, 1, 3, 2, and so on. Okay. Now, a partition can be represented graphically. So in this talk, we are more interested in the combinatorics aspects, especially uh, how Young diagrams and other things are presented here. So the Young diagram is a way of representing the partition graphically, where each of these parts, lambda i's, called cells, will be arranged in left justified rows of unit squares. So lambda I will be the part in the ith row. So now if we consider, for example, this partition 8, 7, 7, 5, 3, 2, 1, then you have 8 cells in the first row, 7 cells in the second row, and so on. And the size of this partition is 33, as you can see. Okay, now for any partition pi, we consider the Young diagram and fix a node. So we say we fix the ijth node, that means the cell in the ith row and the jth column. And we call this the ijth node. Now we define hook difference at this ijth node. So the hook difference is the total number of nodes or cells in the ith row minus the total number of cells in the ith column. For example, if we consider this Young diagram 5 plus 3 plus 1 of this partition 9, a partition of 9, then the hook differences at each node are labeled in this way. So for example, if we look at the node or the cell in the second row and the second column, then there you can see there are three cells in the second row and two cells in the second column. So that's why the hook difference is 3 minus 2, which is 1. So this is slightly different from what we know as hook length actually. So hook length is something that we consider to the right and below and consider itself. But here, and also it's the total number. But here it's a hook difference. So we consider something which is also to the left and something which is also to the top. And then we take the difference. Okay, so this partition 531 shows its Young diagram with labeled hook differences. Okay, so now we define diagonal of a partition. So we say that ijth node lies on diagonal C if I minus j is equal to C. For example, these are the diagonals that we have. We have a main diagonal here, and then we have a diagonal which is so the main diagonal is labeled 0, or we call this the 0th diagonal. And then we have minus 1th diagonal, minus 2th diagonal, and so on. And similarly, below 0, we have the first diagonal, second diagonal, and so on. Why is it so? Because this is node 1, 1. This is node 2, 2. So that's why the difference is of I minus j is 0 here. This is node 1, 2. This is node 2, 3. So that's why the difference is minus 1, and so on. Okay, so now you can ask, like, what are hook differences on each of these diagonals? So for example, if you have 2 and 1, so that's why the hook differences on the 0th diagonal are 2 and negative 1. Okay, so now I will fix some notations which we will be using throughout this talk today. So, and these are also, I'm sure, known to pretty much all of you. So we fix non-negative
Right.
integers.
Yeah.
Hello?
Yes. So can you go back?
Yes.
Uh,
Yeah, sure.
so you said that uh, the I mean on the main diagonal because it was 2 and 1, you get 2 minus 0 and 0
No,
minus 1.
no. So the numbering of this diagonal is coming from the node. So this is the 1 1th node. So
Yes.
that's the first row and the first column. And
Yes.
similarly, this is the 2 2th node, the second row and the second column. So
Yes.
that's why C, which is 0 here, is 1 minus 1, which is the same as 2 minus 2.
Yeah, that I understood. But then you also compared that with
Oh,
the previous.
okay, sure. So now then I said that we now have hook differences on each of these diagonals.
Mm-hmm.
So the hook difference on the 0th diagonal, there are two hook differences. So one is coming from this cell and the other one is coming from this cell,
Okay.
which is 2 and 1.
Yeah.
And similarly, for the minus 4th diagonal, the hook difference is 4.
Okay. Oh, somehow I
Yeah.
heard 2 and minus 1, so I was not clear.
Oh, no, no, no. Yeah.
Okay. Yeah.
Okay.
Okay. Yeah.
Yeah. Okay. So we can define the conventional or standard Q Pokemon or Q shifted factorial notation in this way. So we consider the variable A with index L, which is A considered with base up to L, which is this finite product of 1 minus A, 1 minus AQ up to 1 minus AQ to the L minus 1. And then when absolute value of Q, so Q will be a complex number here. Well, when the absolute value of Q is less than 1, then you can consider this limit as L goes to infinity uh, of this finite product. So you get this infinite product, which where we require this absolute value of Q less than 1 for absolute convergence. Now, Mn, if they are integers, we can define this Q binomial, or sometimes it's referred to as the Gaussian coefficient, as which you read in this way: nq choose m, which is this ratio of q Pokemon symbols, qn over qm times qn minus m, where m lies in the range 0 and n. And if m falls outside this range, then it's 0. It's defined as. Now, for mn greater than equal to 0, m plus n q choose n is it can be shown to be the generating function for partitions into at most n parts, each of size at most m. And also by conjugation of partitions, you can show that m plus n q choose n is, I mean, you can anyway show m plus n q choose n from the definition that it's m plus n q choose m, which is again now the generating function for partitions into at most m parts, each of size at most n. And this phenomena can be explained by conjugation of partitions. Okay, so now throughout the rest of the talk, I will be denoting P of Q greater than equal to 0 as a power series P of Q in Q, which has non-negative coefficients. So whenever you see inequalities with like Q series greater than equal to something or greater than equal to 0, then it's always meaning that each of these coefficients of this Q series are greater than equal to 0, or that particular thing, whatever it is in the context. Okay, so now we go back to some history. So in 1987, George Andrews, Rodney Baxter, David Bressoud, William Burge, Peter Forrester, and Greg Vinod. So all these people, they considered these particular special Q series that you can see here. So it's the sum of this Q exponents attached multiplied with this Q binomial coefficient minus again this Q exponent multiplied with that Q binomial coefficient. And this is defined to be d sub ki of nm alpha beta q. So the parameters are nm alpha beta and ki. And you can also see the way this is defined. The mn, they don't appear in the q exponents. They are appearing just in the q binomial coefficient. Now, Andrews and others, they showed that this is the generating function of partitions, of some class of partitions. And what are they? They are partitions with at most m parts, each of size at most n. And the Hooke differences on the 1 minus beta diagonal of such partitions is at least beta minus I plus 1. So that's a lower bound on the Hooke difference on a particular diagonal. And on the alpha minus 1th diagonal, it's at most k minus alpha minus I minus 1. So that's an upper bound. So that means the Hooke differences are bounded on specific diagonals of such partitions. And they showed that that's the generating function. And also, there are some conditions which were taken into account. So alpha and beta are non-negative integers. I is strictly between 0 and k. N minus m are bounded by beta minus I and k minus alpha minus I. And also, there are added restrictions that the largest part of such partitions, it exceeds m minus I if beta is equal to 0, and the number of parts exceeds n plus I if alpha is equal to 0. So yeah, that was their main theorem of that paper. I think it appeared in the European Journal of Combinatorics. And also, they proved this theorem using recurrences of Q binomial coefficients. Okay, so now if you look at the Q series, uh, these are polynomials. So this whole thing has integer coefficients. So and also since this is a generating function of partitions, as they showed, we have an immediate corollary to that theorem. So the corollary is if k and I are positive integers, where I is strictly between 0 and k, n, m, alpha, beta are non-negative integers, such that alpha plus beta is between 1 and k minus 1, and n minus m are bounded by beta minus I and k minus alpha minus I, then clearly dki in m alpha beta q is greater than equal to 0. And that's because so the coefficients of all these are non-negative because that it's a generating function of partitions. And the important thing to note is here alpha and beta are non-negative integers. So let's see an example. So if we choose k to be 4, I to be 1, n, m to be both equal to 4, and alpha and beta to be both equal to 1, so they are integers here, then the Q series turns out to be this. It turns out to be a polynomial of degree 12 in Q, and the coefficients are all non-negative. And if we look at this particular uh, term q to the 6, it has a coefficient of 2. So, and it's marked in red. So that means if we look at it in terms of what set it is enumerated by, then the set of partitions of 6, whose largest part is at most 4, which comes from n, number of parts at most 4, which comes from m, and all hook differences on diagonal 0. Now the diagonal is here just 0, and we are not considering two diagonals because the theorem says 1 minus beta at diagonal and alpha minus 1 at diagonal. So these are both 1, so that's why they are 0 here. So now the restrictions coming from on of hook differences are coming from these particular bounds here. So once you substitute that, the hook differences are all equal to 1. And there are only two such partitions which obey these properties, and they are namely of 6, and they are namely 4 plus 1 plus 1 and 3 plus 3. So that's why the coefficient is 2 here. And similarly, you can enumerate the other ones and verify yourself. Okay, so now we now go back to 1996. So that's pretty much like 9 years later. David Bressoud, what he did is he considered a special case of this particular general Q series. So he considered the case where I is k and k is 2k, and nm in alpha beta in general with these conditions that you had, and also alpha beta are in general here. So we will see something now. So he defines this to be G N M alpha beta KQ. And then once you do that, you can rearrange this difference of these two Q series as this single Q series in terms of these alternating sums. And now Bressoud's conjecture is if K is a positive integer, N M. Now the difference here compared to the last one is, in the last one we had alpha and beta to be non-negative integers, but Bressoud's conjecture says alpha k and beta k are non-negative integers. So there is no need that alpha and beta are integers, no requirement that alpha and beta are integers. However, alpha k and beta k are integers. So for instance, alpha can be some, the denominator, alpha can be some fraction whose denominator divides k. Now, and also these restrictions are following from the original restrictions due to Andrews and others. Then his conjecture is the G function is now a polynomial in Q with non-negative coefficients. So here is the remark that in the above conjecture, alpha and beta need not be integers. And so now, since they are need not be integers, that means we can't construct partitions with hook differences, right? Because that means the diagonal should be fractional now or something like that. So we don't know what it is. And so it's not clear partition theoretically why this is non-negative. Okay, and so then came a famous conjecture due to Peter Borwein. So in 1990, let me give you a short history. So in 1990, Peter Borwein wrote George Andrews with three conjectures which concern non-negativity of coefficients of some polynomials or finite Q products. And this was his first conjecture. So for the moment, let's define An of Q, Bn of Q, and Cn of Q. So An of Q is this particular polynomial, G polynomial, where you have nm to be n, alpha is 4/3, beta is 5/3, and k is 3. Then his conjecture is this is greater than equal to 0. Bn of Q, n is n plus 1, m is n minus 1, alpha is 2/3, beta is 7/3, and k is q. And his conjecture is this is also greater than equal to 0. And Cn of Q is n is n plus 1, m is n minus 1, alpha is 1/3, beta is 8/3, and k is 3. And this is also greater than 0. And these were recently proven in 2022. I think the work started in much before. So Chen Wang, who was a student of Christian Kragenthaler, he presented this in the burnt. I don't know if someone is in the audience may
So
uh,
Andrews is 80.
clarify. Andrews is 80. Okay, yeah. So that's in 2018 then. Yeah. So he presented these there, and it came out in the advances in 2022. And in the same year, Wang and his advisor Kretzenthaler, they both also proved the same and followed with some more general conjectures using other techniques. In overall, they are all resorting to analytic techniques.
So you mean
But
different proof? Because Chen
uh,
already proved it, right?
yeah. So what Wang did is himself in the advances paper is he looked at these polynomials representations due to Andrews, and then he resorted to proving non-negativity of one, which gave the non-negativity of the other two due to these recurrences of Andrews.
Okay.
So Andrews gave some recurrences of AN, BN, and CN interrelating each other. But Wang and Kretzenthaler, they both wrote another paper in the same year where they were looking at these products, not these sum sides, the sum representations. So they looked at these products and then they were looking at contour integrals of these products to prove non-negativity of the coefficients.
Okay.
So that was a different technique. And that technique helped them to look at proofs of other general conjectures, like not only for the cubic one, but for like mod 7 and other things. Okay, so now the question is, which remains open, is what can be an analogous statement for the non-negativity of this general Q series, which is this, when K is not equal to 2i, when K is general and I are general, and alpha and beta are still non-negative integers. So this is when Professor Berkovich and I gave this conjecture last year. So let's see what it is. So if K and I are positive integers, where I is between 0 and K, N, M. Now, before we had alpha K and beta K to be non-negative integers in Bressoud's conjecture. Now we propose that alpha I and beta I are also non-negative integers, such that the two same conditions hold, which were also given by Andrews and others. So alpha plus beta is greater than equal to 1 and less than equal to K minus 1, with this exception where you have a strict inequality, and n minus m are bounded below by beta minus I and above by K minus alpha minus I. And with these conditions and those restrictions, the D function is now in general a polynomial in Q with non-negative coefficients. So let's see two examples. So let's consider A to be 0 and 1. Then for non-negative integer n, we considered the case where K is 6 and I is 2. So that's clearly K is not equal to 2i. N plus a n 1 half Q. Then once you write it as the difference of these two Q series, you can actually write it as a single Q series using this legendary symbol modulo 3 notation. And so this is greater than equal to 0. That's what we saw. But it's not clear why this is greater than equal to 0 directly without going to this conjecture. And similarly for D9, 3, why is it not clear? Because the legendary symbol can also take negative values, right? And also D9, 3, n plus a, 2/3, 1/3 Q, can also be written in a similar way. And that's also greater than equal to 0. Like, for example, if you choose some value of n, let's say 4, and a to be 0, then that's the Q series that we get, the polynomial. So all the coefficients here are non-negative. So it might be a good exercise to prove why these two are non-negative. Okay, so now what we did is we proved some special cases of this conjecture. So we proved we considered some infinite hierarchies of identities of these D functions, and we showed that they are non-negative. But we resorted to some techniques of Berkovich and Warner, which they call the positivity preserving transformations, and we will see now what they are. So here is a result. So we consider some parameters, non-negative integers LT, positive integers P prime, where P prime is greater than P, and an integer n greater than equal to 2. Then this is a D function which is greater than equal to 0. So the K is now this particular integer, the I is that particular integer here, and that's our capital N, that's our capital M here, and it's sort of nice that it's sort of following some sort of symmetry here. And that's the alpha that we have, and that's the beta that we have. And as you can see here, the denominator is a 2 to the n. Here also in alpha, and in beta also the denominator is 2 to the n. And it doesn't divide what we have in the numerator. So this is a fraction. And also, r should be between 0 and p, and s should be between 0 and p prime. Then you can actually verify, considering these particular choices of parameters, that this is consistent with our proposed conjecture by checking the conditions that we have in the conjecture. So let's see a proof of this. So first we consider a lemma uh, for non-negative integer L and parameters positive integers p prime, where p prime is greater than p. D p prime is of these choices of n, m, alpha, beta. Now here alpha and beta are integers. So we are starting with integers p minus r and r. So this is that particular Q series. And here r and s are integers, where again, the same thing that we have here, bounds. Then it's clear to see that this lemma is actually following from the corollary which we saw was given by, which we saw followed from the theorem due to Andrews and others. So the corollary immediately was the fact that since it's a generating function of partitions, so the D function is non-negative. And here we can see that the alpha and beta are non-negative integers. So clearly this is greater than or equal to 0. Now what we do is we apply another particular sum or a Q series of this form to the D function that we had here. And then we take sum over all k. So we consider CLK of Q, which is the sum over all m from 0 to L, Q to the sum of two triangular numbers times these product of Q binomial coefficients. And the way this is defined, this is clearly greater than or equal to 0. So we are multiplying the D function with something which is non-negative and taking sum over all k. And we show that once you do that, you end up with Q to the sum exponent times another D function. Now, the new D function that you obtain has transformed its k from p prime to 2p prime and I from s to 2s. And the n and m are now integers, but the alphas and betas are now having 2's in the denominator. And of course, in general, these alphas and betas are not integers. You can say that 3r plus 1 over 2 is an integer when r is even, but it's not when r is odd. When r is odd, it's integer, but it's not when r is even. So it's not obvious. But since this was non-negative and that was non-negative, we end up with something which is non-negative. So that's why the new D function that we obtain is non-negative. Okay, so why is this true? Why do we obtain a new D function? So this is following from what we call a positivity preserving transformation due to Berkovich. So this is the theorem that we have, or the transformation. So we consider a Q binomial coefficient of this form, K choose floor of K minus A over 2. Now did I write L to be an integer? Yeah, there it is, 12. Okay, so now when you take sum over all K with C multiplied with that Q binomial coefficient, then the rule is you get a Q exponent like this, but the Q binomial coefficient now transforms itself to another Q binomial coefficient of this form, 2L plus 1 and L minus A. So you get something in the top entry of the Q binomial coefficient, which is an odd number. So this was the first transformation, and we call this transformation C. So the work of transformation C is to convert a Q binomial coefficient of this form to another Q binomial coefficient whose top entry is an odd number. Now we go to another transformation, which is transformation O, and this was due to Berkovich and Oli Warner in 2005. So the first one was given by him in 2020, actually. in a discrete math paper. And this one was a paper in the transactions in 2005. So this transformation O, what it does is it now transforms a binomial coefficient with an odd entry, upper entry to a binomial coefficient with an even upper entry. So from a 2k plus 1, you get a 2l now, along with some q exponent outside. And here is the O polynomial that you multiply it with. So O is this polynomial where you have the sum of two triangular numbers here times the product of these two coefficients. Okay, so now we saw the action of C on D. We obtained a new D, which is greater than equal to 0 here. Now what we do is, in that new D, we now multiply with this O. Why? Because if you look at the new D, then once you add these two, you have a 2l plus 1. So you obtained if you write this as a sum, you will see that it's a binomial coefficient with a upper entry 2l plus 1. So once you apply the O polynomial with once you multiply the O polynomial with that and take sum, you end up with L plus 1 plus 2r minus 2s and L minus 1 minus 2r plus 2s. And that is justifiable because if you add these two, you get a 2L. So you end up with an even upper entry Q binomial coefficient. And also, like before, the 2p prime transforms itself to a 4p prime and the 2s transforms itself to a 4s. And the alphas and betas are now changed. So you can see the numerator is different for both. And the denominators are now 4 instead of 2. Now, since this was non-negative and the O polynomial is non-negative, which is this, it's clearly non-negative the way it's defined. The G function that you now end up with is non-negative here. Okay, so now what we do? So we now go back to another transformation due to Warner. It dates back to 2003. So here, what Warner does is he obtains a Q binomial coefficient from a Q binomial coefficient where the entries are both even now. And this suggests that you can apply this particular transformation W in an infinite number of times. And the way W is defined is this here, which is clearly non-negative. So what we did is we considered this particular D function that we have, and we applied W to that an n minus 2 number of times for n greater than equal to 2. So we end up with this particular D function here. And clearly the K and the I, as you can see, was changed from P to 2P to P prime to 2P prime to 4P prime is now a 2 to the NP prime. And the denominators of the alphas and betas are now 2 to the n, and the n's and m's also involve some factors of 2 to the n in them. And this is the case t equal to 0 in our theorem. So how does the t appear now in this particular family? Okay, so now we again focus ourselves on another transformation due to Berkovich and Warner from that same paper of 2005, but it's slightly different in a different flavor to what we saw in the C, O, and W transformation. So what we have here is a Q binomial coefficient with an even upper entry, but the base is now a QQ instead of a Q. Previously, all these transformations were changing from base Q to Q, Q to Q, and here Q to Q. But here we now have a Q cube, and we obtain a new Q binomial coefficient with base Q, but the J changes to a 3J. And the Q exponent also has a factor of 3 coming in front of it. So what's this polynomial that we are multiplying it with? So ALR of Q is this, which is greater than equal to 0. Now, you may argue that this is, or you may see that this is clearly not, I mean, it's not clear why this is non-negative. However, this 1 minus q to the 2l divided by this q sub l minus 3r, and once you write it in some other form, we will be able to use a theorem due to Andrews, which show that such polynomials are non-negative. And I haven't stated that here. So we can show that this is non-negative anyway. So now we have this d function here, which depends on n. You now change Q to QQ, of course, because we want a Q binomial coefficient with base QQ. So first we do that, and then we apply the transformation A on that. Since this was an even upper entry, if you add this to, you get a 2L. You can apply that as many number of times as you want. So we apply T times, and we end up with the result that we have here. So we end up with this infinite hierarchy of identities, which is non-negative. And this is one particular result which uh, which obeys our conjecture. Now let's look at a second result. So the scheme for the obtaining the first result was you apply C, then you have O, then you have W some number of times, and then you apply A some number of times. Okay, now that's the second infinite family that we have. Here also the K and the I look similar, but the N, M, alpha, beta are slightly different. And this is also consistent with our proposed conjecture by checking the conditions that we had in our conjecture. Okay, so we obtain with the same starting point and we apply C to that. So we have that. Now what we do is we don't apply O and W straight away. We now apply, now since this is a 2L plus 1, right? So these two are, when you add them, you get a 12 plus 1, which is an odd number. So now we consider another positivity preserving transformation due to Berkovich and Warner, which is similar looking to the A transformation that we have, but here the polynomial that we are multiplying with, by the way, these are sometimes called kernels of transformations. So we are multiplying it with this kernel here, which is slightly different because we had a 2L there, but this has a 2L plus 1. And we had a L minus 3R there. This has a L minus 3R minus 1. So once we multiply that with some Q binomial coefficient with base Q cube, but with an odd upper entry, 2R plus 1, we get another Q binomial coefficient with the same odd upper entry. The parity is preserved now. So what we do is we change Q to Q cube at the starting point after applying C. And we now apply A tilde to that, let's say T number of times. So we get this particular family here, depending on T. And now we apply O, the O transformation that we had, followed by the W transformation n minus 2 number of times. So we end up with the result. So the scheme is now changed. So first we applied C, then we applied A tilde T number of times, and then we applied O, and then we applied W, n minus 2 number of times. So we end up with this result. Okay, so these are the two infinite families of identities that we have, which justifies our conjecture. And I believe there might be many more identities which can be proved of many more families of non-negative Q series identities which can be proved to justify our conjecture, which are still yet to be found. Okay, so these, by the way, this way of using transformations is not used so much before actually. Just that we saw that this is applicable to such identities which have Q binomial coefficients. But if you want to prove results like this combinatorially, then it might be very difficult. At least for these two cases also. And a combinatorial proof of Borwin's conjecture is still open to that. Okay, so now we look at some applications of cubic binomial transformations. By cubic, I mean a transformation which changes a Q binomial coefficient with base Q cube to Q. Okay, so in an attempt to prove Borwin's first mod 3 conjecture, Andrews in his 1995 paper gave these three polynomial representations. So an of Q, you saw that it was this particular G function here, which is this. So you can light it as an alternating sum of Q binomial coefficients with some Q factor outside. And similarly for Bn and Cn. So Andrews showed that those are equal to each of these polynomials. Now, if you look at these complicated looking polynomials, it's not clear also why these are non-negative the way they are defined. I mean, of course, the denominators will give you non-negative series when you expand as power series. But look at these particular polynomials here. So you have 1 minus q to the 2n, these particular factors, and then you have something like this and something like this. So they are not clearly non-negative. But but these were equal to the ones that I showed you before. Okay. And in the same spirit, Professor Berkovich and I, in a recent another work of ours, we showed some other polynomial representations of identities which are non-negative and which follow from the G function. So these are the results that we have. So these right-hand sides that you see here are looking quite analogous to the G functions which we have for Borwein. But the left-hand sides here, they look they resemble close similarity to the ones which Andrews have. Slightly easier, I would say, because Andrews's factors are more involved here. But they are also not clear why they are non-negative, because we get something like 1 minus q to the 2n plus a, for example, in the first result. And also we have an alternating minus 1 to the j here. And similarly, we have something like this, minus 1 to the j, 1 minus q to the 2n. So these two are such results. And also we have two more. And the all these right-hand sides are non-negative because you can write them as G functions in terms of n, m, alpha, beta. And the alpha, beta are integers. So that's nice. But the left-hand sides, we are not sure why they are non-negative themselves. Okay, so let's look at proofs of all these four identities. There are six, I would say, because the first one is with a equals 0 and 1, and the last one is also with a equals 0 and 1. So yeah, we have six. So our starting point is what we call Rogers-Jacob polynomials. So Rogers and Jacob, they define these polynomials where you have uh, these coefficients of the polynomials to be these q binomial coefficients, n, q, choose j. Now, if you substitute, so let's say it's a polynomial in t and q. So if you substitute t equals -1, then you can show that this is equal to q square n. And similarly, when t equals -q, it can be shown that this is equal to q with base q square sub floor of n plus 1 over 2. And I think the first one is an exercise in Andrews's book, or the theory of partitions. It might be in the chapter 1 exercise. Okay, so the first one is this. And now, since this is starting from 0 to n with n choose j minus 1 to the j, you can rewrite this like this. So you can rewrite it as minus n to n, minus 1 to the j, 2n choose n minus j. And once you do that, you will also have an extra factor of minus 1 to the n. So that's the identity that we obtain. Now we substitute q go to q cube here. We replace q with q cube. Why do we replace q with q cube? Because we want something which resembles cubic, so that we can use a cubic positivity preserving transformation on this. So that's our seed identity. And once we have q cube here, we can now apply the transformation A, because the upper entry here is even. So once we apply transformation A once on this identity, we get the left-hand side of this with A equals 0. So that's the proof of the first one. Now in 2, which is this, we replace n with 2n plus 1, and we also interchange summations. So j now is from minus n minus 1 to n. We have minus q here, so this will be minus 1 to the j q to the j as it's here. But the upper entry now is odd, and the right hand side is now a product like this with these factors. So again, we change q to q cube, and we apply now transformation a tilde because the upper entry is now odd. So let me quickly remind you the transformation a and a tilde. So a was this transformation, we changed a 2r to a 12, and a tilde was this transformation, we changed a 2r plus 1 to a 12 plus 1, along with these factors outside. So we get the first theorem that we have here with a equals 1. So that completes the proof of the first identity. Now, for the second one, which is this here, so this doesn't involve a. So we change n to 2n in 2, which is this one. So if you change n to 2n here, this one becomes an n plus 1. So you get, sorry, that one becomes n. So you get j from minus n to n, minus 1 to the j, q to the j with that q binomial coefficient. And you have minus 1 to the n, q to the negative n, q square n. And now once you apply q, go to q cube here, the same thing, and transformation a once, you get this identity here, the left hand side. Okay, now what about theorem 5 and 6? So now what we do is we have theorem 3 and 4, the first two sets, the first three identities, the first set of the two identities and the next one. So we apply q going to q inverse in 3. So when you apply q go to q inverse here, that means this q binomial coefficient becomes now with base q inverse. You can use the formula which is given at the end of Gaspar and Riemann, that if you have a q binomial coefficient n choose m with base q inverse, it's q to the degree times n choose m, the degree of this q binomial coefficient times n choose m. So you have an additional factor here. So you get this times q, this is equal to q square n. And this particular identity, which looks very nice, was also obtained by Andrews in 1991 uh, in some other context. So he was doing Gaussian sums, and there he obtained this identity. Okay, now when you substitute q with q cube here and apply transformation A again, because it's a 2n now, we get the identity that we have here. And similarly for the last one, we apply q go to q inverse in the fourth one, which is here, and again q go to q inverse in the fifth one here, and you obtain this identity and that identity using that formula in Gaspar and Riemann. And once you apply q go to q cube and transformation a tilde for the first one, because this is with a 2n plus 1, you get theorem 6, the last identity here with a equal to 1. And when you apply the transformation A, you get theorem 6 again with A equals 0. So these are the two things. So we saw what we got with just the Rogers-Jacob polynomials special values and reindexing these summations, and then applying the transformation A and A tilde. And we also saw what happens when Q go to Q inverse and we do the same technique. So we end up with these analogous polynomial representations. So it would be nice to check, find such more such identities. And okay, so that's pretty much it for the talk today. And so here is an open question. So far we have seen that we have used quadratic and cubic positivity preserving transformations, by which I mean the bases changing from q squared to q and q cube to q. Now it would also be nice to find quintic positivity preserving transformations. That means where you have a change from q to the 5 to q base. And also you will have something like that the things here. Let's say you end up with something like this, but with a 5j here, or maybe some exponent which involves the 5 factor. So yeah, it would be nice to look at such transformations which are not yet found in literature. So here are the references. So this is the paper where Andrews obtained that identity, partitions and the Gaussian sum. And this is the main paper by Andrews, Baxter, and others, partitions with prescribed hook differences. Okay, and that's pretty much it. Okay, so this is Chen Wang's famous paper, Analytic Proof of the Borwin Conjecture in Advances. And that's Wang and Krethinthaler's paper, An Asymptotic Approach to Borwin Type Sign Pattern Theorems. But it's still in the archive since 2022, so I don't yet know if it's published or not, actually. I don't think it's published. Okay, and with that, I would like to thank you. And so these are the two papers of ours. Okay, any questions?
Yeah, thanks, Aritram. Yeah, any questions for him? So I had one question. So you mentioned about three identities Andrews derived for A sub n of q, B sub n of q, and C sub n of q.
Sure,
And
yeah.
words proving Borwin conjecture. I think his goal was to prove Borwin.
Exactly.
So
But
where
he ended up with such representations.
yeah. So where does the difficulty occur? Like in words proving the Borwin conjecture using that approach? Do you know?
Okay, let me check. So as far as I know, these things. So he expanded this, and he he tried to obtain some positive. I mean, he obtained these recurrences, right? But even those recurrences which follow from these have summands which are not. I mean, have factors which are non-negative, which are negative. So, I mean, you may have something like an is equal to some factor of some polynomial of q times bn minus some other polynomial of q times cn. So they were not clearly non-negative. I mean, if he had some non-negative recurrences, he could have directly shown. But what Wang did is he wrote one of those. I mean, you can show that if you have uh, if you know the coefficients for Bn of q, you can find the coefficients of Cn of q. That's how it is defined, because the Borwin polynomial is q3n over q cube q cube n, which is an of q cube plus q times Bn of q cube plus q times q square times Cn of q cube, right? So the periodicity is obtained from that. So Wang actually wrote one of those in terms of the other and showed non-negativity for the first uh, of those coefficients. The first few, I mean, he showed non-negativity eventually after some number, and then he checked the non-negativity up to that particular thing.
Mhm.
But
So,
but it's not clear how this, I mean, what obstruction is following from that.
so in your identities where you have similar representation,
Yes.
so do you face the same difficulty towards proving Born type conjectures?
No, so we don't know whether the products that we have, the product sites that we have here are actually like you have some result like the Borwin thing at a trisection or something like that. I mean, we have to then find such products which are, I mean, for example, we have to find such A and B and C N type things, products which can be combined to give a product of like that, which will give us Borwin sign pattern theorems. But these are some random results. So
Okay.
once we find such things, then we can write it as a product, check and write it as a product, and then we can try to prove.
Okay.
Yeah,
Okay.
but I mean, for this one, I don't think it can be written in that way. So that was also actually one of our questions. I mean, it's also a project that we were looking at some point. So we tried to obtain other such polynomials which can be combined using some relation, so that that gives us a product, and that like borrowing, and we can prove it or using asymptotics at least. But we haven't found so far.
Okay.
I think it can be found for some other modulus maybe. Not sure.
But are such conjectures known for other moduli?
Yeah, so recently Professor Berkovich and I actually have given some Borwin type sign pattern theorems, which were actually inspired again due to the work of Wang and Kretenthaler.
Mhm.
So there, the sign pattern is not like a plus minus minus plus minus minus. So we have some. I mean, of course, the first one, n of q cube, we have something like that, which is always positive. But then we have some sign patterns which are always positive up to a number, up to a threshold, and then beyond the threshold we have negatives, and then again positives and negatives. So it alternates more frequently. It's not something which is consistently negative.
Oh, okay.
And even Amdebarhan, I think, had some results like those. Yeah,
Interesting. Thanks. Yeah.
yeah,
So,
Any
sure.
other questions?
yeah, I wanted to ask. So Michael Schlosser has proved recently such results. Unfortunately,
Okay,
he has a
yeah, sure.
throat infection, so he can't
And
speak.
he's in the audience, I see.
Yeah, yeah. But so did you examine those kind of things? Are they related? And also, Michael and I had a set of Borwine type conjectures for
Yes, I
products.
saw your paper.
Okay,
Yes.
so those things
Yeah.
also don't seem to fit here, is it?
But I haven't seen Professor Schlosser's recent paper. I have to check.
Okay. So
Sure.
yeah, so there is some activity I think which is happening around these where there are products, but from what I
Okay.
understand, this is not
Okay.
these are not necessarily products what you have. But in any
Yeah, yeah,
case,
yeah. Mine ones. correct.
Yeah. In any case, can you send me your slides? They're very interesting for
Yeah,
some
sure,
other
absolutely.
project, which I will tell you later. Huh?
Sure.
Okay. Thanks.
Any further questions? If not, let's. Yeah, Rohini, you have a question. Yeah.
Yeah. So in the transformation that you're using, in that
Sure.
like the
You mean which
changing to
one?
even and changing to odd. Um,
Okay.
so in that the powers of Q are changing very arbitrarily. So when we are combining the terms, I didn't follow exactly how like this would be useful.
Oh, sure. Okay. So what you do is you write first these D functions as sums of alternating sums, right? Of these differences of Q binomial coefficients. And so what you do is you apply this transformation O, let's say, for example, in this one, it's O. And when you apply that on those particular Q binomial coefficient, you can use these transformations to that to end up with these particular right-hand sides. And then you will have these right-hand sides minus some other thing. And then you can check that that can be written as a D function using the definition.
Okay, so you kind of applied twice.
Yeah, exactly.
Okay,
As it
okay,
is
sure.
required.
Yeah.
As it is required. Yeah, exactly. Sometimes it may be
Okay.
twice or it may be more than twice.
And so when you do from even to even and you apply it as
You
many
can apply any number of times as you want.
2 raised to n.
Exactly. That's how the 2 raised to n comes.
But the sum of like two odd integers is even. Does that not cause any problem?
We don't have sum of two odd integers. We always have, if you look at these D functions, then the n and m's are always either L plus something, L minus something, that same thing which gives you a 2L, or you have a L plus 1 plus something and then L minus that thing which gives you a 12 plus 1. But you don't have something like a 2L plus 1 or a 2L minus 1 here to give you an even. I
Okay,
mean,
so parity
if
is always
such,
present. Okay.
exactly, if you have something like that, then it would be interesting to see if such a different transformation exists, which I haven't found.
Okay,
Yeah,
thank you.
that's the case which we don't know yet.
Any other questions? If not, let's thank